Hello everyone, and thank you very much for giving me the opportunity to give this talk. My name is Yana Husanova, and currently I'm working in Max Planck Institute for Astronomy in Heidelberg. And today I'm going to present the work I've done during my PhD together with Mathieu Betterman and Olivier Lefebvre and ALPINE collaboration. So the topic of my talk will be the dust hidden star formation rate density at redshifts above 4. And first of all, let's discuss how do we measure star formation rate density. So to measure star formation rate, we need to measure the light from the young and short-lived massive stars. We can measure from the UV light, but since some part of this light is reprocessed by dust, we need to also measure the dust obscured part, which manifests itself in the infrared. And if we know the UV luminosity density and infrared luminosity density, we can easily derive the star formation rate density as a sum of these two contributions and using some conversion factors. However, we don't always have the information about the infrared luminosity, and therefore we can use some dust corrections or emission lines. The easiest way to correct for dust is using the IRX-beta relation, where IRX is the ratio of infrared luminosity to UV luminosity, and beta is the UV continuum slope. And this relation works very well in the local universe, where the local galaxies follow the Calzetti attenuation law, but it's very uncertain at high redshifts. We can see from many works that this relation evolves with redshift, and also at high redshift there is a larger scatter of this relation. So what can we do? Ideally, we would like to have the rest frame far infrared data and a good constraints on the infrared luminosity of galaxies, which is a crucial part of constraining the star formation rate density. But unfortunately, up until now, these constraints were very uncertain and the results were inconclusive, since it's quite hard to get a large sample observed in the rest frame far infrared, and therefore the ALPINE survey was built with the goal to get the constraints of this star formation rate density hidden by dust at redshifts above 4. The galaxies were chosen from spectroscopic surveys such as Deimos and Woods, and since all these galaxies have spectroscopic redshifts, we could ensure a high detection rate of C2 luminosity. But since the survey was built in order to get the C2 luminosity, the detection rate of far infrared continuum is lower, but it is still possible to get constraints from the observations of far infrared continuum. And also, this survey is very good to constrain star formation rate density, since it covers a very large range of properties such as stellar masses, FU magnitudes, and star formation rates. And based on UV data, we can see that these are the galaxies which are on the main sequence. So, what can we do if we have this low detection rate of far infrared continuum? We can use the stacking and derive the average properties of galaxies, even if they are too faint to be detected individually. We combine the galaxies with similar properties, and we can measure the average far infrared flux of these galaxies. To measure the flux, I used the free arcsecond aperture to get all the flux from the galaxies, even if there are some maybe small offsets from the phase center, and the uncertainty of the measurements is estimated using the bootstrapping. As you can see on these example images, as we go to higher stellar masses, the far infrared flux is also higher. And this we can use as a proxy for the far infrared flux. How do we determine the infrared luminosity density using these stack images? So first of all, we do the stacks in the bins of stellar masses. We measure the flux on the stacks images, and we can find the correlation between the far infrared flux and the stellar masses. And we need to add to it the information about density. And this we can get from the literature. We can use the galaxy stellar mass functions to determine the density in each bin, and then we can just convolve these two functions and we can get the infrared luminosity density. And if we extrapolate it to lower and higher stellar masses, we can get the total infrared luminosity density, which can be then converted to star formation rate density. And of course, we can also use other proxies of the far infrared flux. For example, we can use the FUV magnitudes. And the UV luminosity functions we can also get from the literature, since they're quite well constrained in these redshifts. The main caveat here is that using just one point in the rest frame far infrared, we need to get the total infrared luminosity. And for that, it's necessary to use some spectral energy distribution templates. And there are several of them available in the literature, and the results will depend on the template. To choose the templates, I used the stacks of Herschel data available in Matthew Betterman's paper, and I only chose templates which have the reduced chi-square values below 1.5. And from each template, we can calculate the conversion factor from far infrared flux to infrared luminosity. And then if we have a number of templates, we can derive the average conversion factor and the uncertainty on this conversion factor, which can be also propagated to the uncertainty of the star formation rate density measurements. As you can see, we can observe the correlation between infrared luminosity and stellar masses, as well as between infrared luminosity and FUV magnitudes. And this, of course, can be used to constrain the star formation rate density. And these are final results. So I show in the with the orange symbols the constraints of the infrared component of star formation rate density, and in the blue the constraints of the UV component of star formation rate density, and in red the new constraints obtained from ALPINE, with constraints with the mass as a proxy as a star, and constraints with the FU magnitudes as a proxy as hexagons. As you can see, with both proxies, the results are fairly consistent with each other within the error bars. You can see that at redshifts below 3, the infrared component of star formation density is clearly dominating the UV1. And it was expected that at higher redshifts, these two curves will cross eventually. And some works which were attempting to constrain the infrared contribution claimed that already at redshifts above 4, the infrared contribution is negligible, as for example the paper of Koprowski in 2017. But with ALPINE we can see that even if we only use the lower limits, which are shown here as red triangles, still we have a very high contribution from the infrared. And if we extrapolate the results, we can see that there is a very high contribution from the infrared. And if we compare the dust hidden contribution to star formation density with the total star formation density at these redshifts, then we can see that the infrared contributes to at least half of the total star formation density. So to conclude, using the stacks of these targeted sources from ALPINE, I was able to constrain the dust hidden part of star formation density at redshifts above 4 and obtain a very consistent results using the different proxies, and also consistent with other works using ALPINE survey. So we start to obtain a more consistent picture of the evolution of the dust hidden star formation density at redshifts above 4. And we can see that dust still is important at redshifts above 4, and at least 50% of the UV light is absorbed and reprocessed by dust at these redshifts. And if you have any further questions, feel free to contact me.